Hey, what's up everyone? Welcome to another episode of HPC in the Cloud. I'm Joe Schoonover from Fluid Numerics. Today we're going to be introducing you guys to a new solution called Cloud CFD. It combines OpenFOAM, Paraview with Google Cloud and some other HPC tooling like the Slurm job scheduler to get you up and running quickly with CFD workflows on the cloud. So let's just go ahead and get started. First, go ahead and head on over to console.cloud.google.com. If you don't have an account, you'll want to go ahead and create one, and you should land on a page that looks similar to this when you're all set up. We're going to go ahead and just launch the solution to start, and then I'll walk you through some other configurations while that cluster is deploying. So if you use that products and services menu up on the top left side, this is the triple bar menu there, head on down to the marketplace. And once you're there, all you got to do is search for OpenFOAM or Paraview or any of the things that are included with this solution. If you hit Cloud CFD, that's the solution you're going to want to be using, and then go ahead and hit launch. And I'll walk you through very quickly how to launch this cluster. So for the deployment name, you can call it whatever you like. This is going to be end up being the name of the controller instance and your login node when those become live. So if you're not familiar with this auto-scaling cluster, essentially you get those two instances, a controller login node. The login node is where you'll access the cluster and schedule jobs through Slurm. So we'll kind of walk through here in a second how to get all that configured. Just go ahead and give this a name. I'm going to call this OpenFOAM Demo and leave the zone and network settings to their defaults. Of course, if you want to pick a zone that's closer to home, feel free to do so. So on the login node, you can just use the defaults for what we're doing today. So we'll leave this at 4 virtual CPUs. That's 2 physical cores and 1 login node to have there. Now, if you have a larger team, you might consider making that login node a little bit bigger by clicking on that drop-down menu and picking a larger core count or increasing the number of login nodes you have available. Down on the controller, again, we're just going to leave that as the default settings. The most important stuff to set up today are the compute partitions. When you deploy this cluster, you get 3 compute partitions, 1 for doing mesh generation operations. Right now we have on the solution Gmesh and PyGmesh available for you. Then we also have partitions for running OpenFOAM and for running Paraview. For what we're doing today, you'll only need 8 vCPUs. So if you click that drop-down menu on the OpenFOAM partition and scroll on up to the N1 standard 8, and then do the same thing for the Paraview instance. There's no real need to have those large core counts for what we're doing today. Of course, if you've got bigger data sets or bigger problems you want to solve, make those instances as large as you possibly can. Since OpenFOAM and Paraview are parallelized with MPI, it's ideal to have those VMs as wide as you can make them. Once you've got those things selected, go ahead and hit deploy. This will bring us to a deployment manager page where you'll be able to keep track of the resources that are created here. While this is provisioning that login node and controller for us, we need to do 2 things. We need to set up the identity and access management permissions so that you can SSH into the cluster. And we also need to configure a firewall rule setting so that you can connect your Paraview client on your local workstation to a Paraview server running on this cluster. And go ahead and click that products and services menu again and head on down to IAM and admin. You'll see that underneath the products panel. Once you're there, click on IAM. When that page opens at the very top, go ahead and hit add, and under new members, you'll put your email address. Now, if this is your first GCP project, you're probably already a project owner, but we do want to make sure that you know the permissions you absolutely need to be able to log in, so that in the future, when you have other users leveraging your cluster, you can apply principle of least privilege. So the first role you're going to need today is Compute OS Admin Login. This will allow you to SSH into the cluster. And it will also allow you to escalate to root. Now, if you have other users on this cluster, you don't want them to escalate to root, you can use Compute OS Login for them. You'll need today that Compute OS Admin Login, and then the other role is Service Account User. Okay. Once you're done there, hit Save. Now, I've already got mine in there, so it says no change on my side, but that will set you up on that. Now what we need to do is head on over to the VPC network firewall rules to open up a TCP port to connect your Paraview client to Paraview server. So if you hit that products and services menu, again, let's go ahead and scroll on down past compute and storage and databases and head on over to networking. If you hover over that VPC network, the sub menu there, you can see we have firewall. go ahead and open up that firewall page, and we're going to create a firewall rule. You can call it whatever you like. I like to name my firewall rule something that's meaningful so I know what it's intended to do. So let's call this allow PVC server TCP. For the network, choose that default network or whatever network you decided to deploy your Cloud CFD cluster to. You can leave all these other options in their default in targets, select all instances in the network, and then for the IP range, you'll want to put your gateway IP address for your office, for your home, or wherever you're doing this from. If you don't know what your IP address is, just open up another tab right now and just type in what is my IP address. There's plenty of course, Google will provide you an IPv6 address if you type that in, but there's plenty of other resources you'll be able to get your IPv4 address, and that's what you want to enter in here for your source IP ranges. Once you do that, down below under the protocols and ports, click on TCP, and then for the port number, put 11,000. That's what we're going to use today. If you do have multiple users on your cluster, you might consider putting a range of ports on here. So you might say 11,000 up to 11,100, for example. This would allow multiple people to have Paraview client server connections happening at the same time. But all you'll need today is just that one port. When you're done, go ahead and hit create. Now I've created one beforehand, so I'm not going to do that. Let's go ahead and check out what's going on with this cluster. Now that we've got the firewall rules and the IAM permissions set up, let's see if we can get into this cluster and go on to the next step here. Essentially what we need to do is get onto the controller to set up the Slurm accounting so that you'll be able to submit jobs. If you look on the top right here in your Cloud console, there's an Activate Cloud Shell button, which, by the way, at this point, the solution is definitely deployed. You can see that by that green check mark up on the top. So let's go ahead and hit that Activate Cloud Shell button on the top. This will open up a terminal in your browser. And now you need to do two things, especially if this is your first time. So one, you'll need to create an SSH key, and you can do that just by running SSH keygen -t RSA and hit enter. Go through the prompts. We highly recommend you set up a password to protect that RSA key pair that's created. Again, I've already created one, so I'm not going to run it. Once you have that key, you'll have a public key stored underneath .ssh idrsa.pub. We want to attach that public key to your Cloud Identity profile so that you can SSH into your cluster. So go ahead and run gcloud compute os login SSH keys, add, and then we'll say key file, and you'll need to give it the full path to that key. Okay. I'll go ahead and run that on my side. And now that we've got those attached, you should be able to SSH into the controller or the login node using OpenSSH. So if you're doing this on your local terminal on your own workstation, the same rules apply there. Make sure you have an SSH key there, and you can attach that key to your profile using the gcloud command. All right, so let's go ahead and SSH into that compute node. Now, if you're having trouble SSHing in, just something you need to be aware of, your POSIX username is actually going to be set to your email address, except you need to replace the @ symbol and the dots with underscores. If you're interested in learning how to customize that POSIX username, definitely reach out to us at support@fluidnumerics.com. We'll show you how to do that. All right, now that we're on the controller, we need to configure that Slurm accounting. We're going to be using a tool called Cluster Services to make that happen. And to run that tool, you need to be root. So go ahead and run sudo su, and then do a cluster services. We're going to list all, which is going to give us a YAML dictionary that describes the configuration of our cluster. This cluster config file, this whole workflow I'm going to show you is basically what you're going to need to be able to do to customize your cluster, your Slurm accounting, and any external file system mounts that you want to attach to your resources. So now we have this config.yaml. What we need to do is append a Slurm accounts block to it that we're going to end up customizing so that you can submit jobs. So you're going to do is run cluster services sample Slurm accounts, and then we're going to append that to the config.yaml. All right, let's go ahead and open up that config.yaml now and jump down to the bottom. So I'll set the line numbering for you here so you can follow along. So what we're going to do is take this empty Slurm accounts specifier on line 85. I'm going to cut it and paste it down below. Okay, Okay, let's get rid of some of that white space and let's remove that empty array. Now on the allowed partitions, we need to basically specify what compute partitions we want to be able to submit to. So let's take a look at what we have available. If you run sinfo, you'll see we have a meshing partition, OpenFOAM and Paraview, right? Very similar to what you saw on that form from the marketplace page. So basically we want to give ourselves access today to the OpenFOAM and Paraview partitions. So let's open up that config.yaml. Okay. And on the partitions, let's change this to OpenFOAM. And let's change this to Paraview. Now for the Slurm account name, this can be anything you want it to be. I'm going to call it CFD since this is going to be an account used for people who want to run CFD workflows on Google Cloud. For the users, you'll just put a list of the POSIX or the Linux usernames that you want to have grouped into this Slurm account. Right now, it's just me, so I'm just putting Joe. Okay, now that that's set, let's walk through the next two steps to apply these changes. So we're going to run cluster services, update Slurm accounts. You're going to give it that config file that you just created and modified. Now let's first preview those changes to make sure we got everything right. So we got the allowed partitions OpenFOAM and Paraview. The username is Joe, and yeah, I do want to name that Slurm account CFD. Let's double check. If I run sinfo, we can see OpenFOAM and Paraview. I got the spelling right. Once you're happy with it, go ahead and rerun that same command and remove the preview flag. Okay. Now, if you want to see what this did, if you're familiar with Slurm, you can run saccount manager list user, and you'll see that you have those users that you just added in that config file under that particular Slurm account. And basically, when those users try to submit jobs, they'll only be able to submit jobs to those partitions that you've specified there. All right, so we're done on the controller. Let's go ahead and exit out of there. Okay, and now let's hop into that login node. So grab that login node IP address, and let's SSH in over there. Now what we're going to do is copy the Slurm batch file we provided for you on this solution. So if you were to take a look underneath apps directory, there's a few things there for you. It basically contains all the packages that we've installed for you. But there's one directory called share that has some pretty useful resources. So one, it's got an OpenFOAM Slurm batch file that we're going to use today to run the NACA0012 Aerofoil simulation. It's also got a Paraview server connection file that we'll use to connect your local Paraview client to a Paraview server running in the cloud. And there's another script there that supports that activity. So what we want to do is copy from app share the openfoam.slurm file into your home directory. Okay, let's take a look at that real quick. We're going to focus on the batch header for now. We're going to get the job submitted, and I'll show you what's going on underneath the hood. Make sure at the top that Slurm account that you have in this sbatch command is set to the same Slurm account that you set in the config file. So I've set it to CFD. Now you can see very purposefully because that's what we have in the default here. And then, of course, we want to submit that to the OpenFOAM partition. This job will run with 8 tasks. So this means we're going to run with 8 MPI ranks to run the simulation. And we'll kind of cover the rest of the details in this file after we get this job submitted. So once you got that account and partition set, just go ahead and sbatch openfoam.slurm. Cool. So if you look at SQ, we've got a job that is currently in a configuring state. It's going to run on the OpenFOAM node 0. So if I were to go up into the Cloud Console again, let's go hop over to the Compute Engine page. So if you hit that Products and Services menu, scroll on down to Compute and click on Compute Engine. Once this loads, you'll see 3 instances here. We got the controller, the login node, which were created from the marketplace deployment, and now OpenFOAM node 0, which is being created on the fly because we submitted a job. When that job is done, after that node goes idle for a few minutes, it will be torn down automatically for you. So while that node is configuring, let's quickly walk through what's going on in that openfoam.slurm file, and then we'll get connected to a Paraview server. Okay, so as I mentioned, we're running with 8 MPI tasks for this job. All the standard out and standard error are going to go to a file called OpenFOAM minus that %J stands for the job ID. Since right now the job ID is 2, we'll have a file called openfoam-2.log that has a standard out and standard error. OpenFOAM and Paraview and OpenMPI, all the things we provided for you are managed via environment modules. So if you were to do a module avail you'll see the packages that are available, and you can use a module load to bring those packages into your path. So at the very top of that Slurm file, you can see that's what we're doing, is we're loading OpenFOAM. Now implicitly, OpenFOAM will automatically bring in GCC and OpenMPI for you. Okay. All we're doing here now is copying the OpenFOAM tutorial for the airfoil. This is the turbulent flow past a NACA0012 airfoil. And then we're adding a domain decomposition file to basically break the domain into the number of Slurm tasks, so the number of MPI ranks. And then down below, we're just running through pretty standard OpenFOAM workflow. We're going to do mesh generation. We do the domain decomposition here, and then we run the job using MPI run to run the row simple foam executable in parallel mode. At the very end, we reconstruct the solution, because remember, in domain decomposition, each MPI rank gets their own subdomain. So each MPI rank ends up writing out its own files. We want to stitch that all back together to make one nice clean database of output. And then to help us with visualization, we just touch this file, NACA0012.foam. It's just an empty file, but it's needed to open up a OpenFOAM simulation case in Paraview. So let's hit refresh on that compute side. You can see that node is up. Let's see how we're doing on the queue. Looks like we're actively running. So if you were to take a look, you see we now got that OpenFOAM2.log and our airfoil simulation. Okay, so while that's running, let's hop onto our local workstation in a terminal and open up. We're basically going to go through getting you set up to connect Paraview to the cloud. So let's open up a new terminal. Let's make that text a little bit bigger for you. That's probably too big. Okay, I'm going to start by just making a directory to store that Paraview PVSC file. Basically, we need to pull that file down off the cluster, and then we'll load it in Paraview, and that will give us a nice, easy-to-use form to be able to connect to the cluster. So I'll make this directory here, Paraview PVSC. Let's grab that login node IP address. Okay, and I want to SCP from that cluster. We want apps share Paraview GCP.pvsc. Okay, and where do I want to save that? I want to put that in that new directory I just created. Yes, that's okay. Let's go ahead and unlock that key. Great. Okay, so now we've got that PVSC file. Essentially, this is an XML file that Paraview will interpret to make it easy for us to connect from client to server. Now that we've got that, let's go ahead and open up Paraview. Okay, and close out that color map editor. What we're going to do now is just open up the memory inspector just so you can keep an eye on what resources we have. So right now you can see I've only got my local client. Once we connect, you'll see the compute node on the cluster show up over here. To go ahead and connect, you'll hit this server connect button up top and click on load servers and navigate to that path where you put that XML file, that Paraview GCP.pvsc. Once you do that, you should see a configuration showing fluid Slurm GCP, and it should be on the localhost server through a reverse connection. So let's go ahead and hit connect. And you'll see right now, so right now this form is primarily configured for Linux. So what's going to happen here, once you hit the connect button, it's going to open up an Xterm window and set up a reverse SSH connection to the login node. The login node will submit a job for you to get the Paraview server started on a compute node, which will establish a reverse connection back to the login node and ultimately back to your local system. So what we need is your SSH username here. We need that login node IP address, so I'll go ahead and paste mine in there. You shouldn't have to change this remote script, but in case you have your own Paraview job submission script, you can swap that out here. Now the server port will be the server port that you use in those firewall rule settings at the beginning of this tutorial. And then everything else down below, make sure that Slurm account is set to the Slurm account in that config file that you set, and then we're going to submit this to the Paraview partition. So let's go ahead and hit OK. So like I said, it opened up an Xterm window. It went into the login node and submitted a batch job to start Paraview server. So let's take a look real quick what's going on the cloud here. If I move that window out of the way, up into the top right, let's refresh this. What you'll see now is we have a Paraview node that's live. If I run sinfo, or let's take a look at SQ, we've got Paraview configuring. Cool thing now is our OpenFOAM job is done. So let's take a look at that airfoil Great. We have all of our output, and we've got a NACA0012.foam file waiting for us to do some viz. I'm just going to leave SQ running and watch here. And while we're waiting for that to come up, let's talk about what we're actually going to be visualizing here. So if you're familiar with this tutorial, essentially what we've got going on is this airfoil that has a 0 angle of attack. We're running at about Mach 0.1 for this setup. And on the left side here, what we have is an inflow, uniform inflow going from left to right. So in this diagram, that's going to be in the X direction. So that uniform inflow, let's call that capital U. Again, it's set up in such a way that the Mach number is about 0.1. I think it's 0.15 actually. And we've got uniform flow coming in here. Okay, and what we should expect to happen here is when that flow encounters that airfoil, you'll end up having a high pressure buildup on the nose. So we got high pressure over here. And according to Bernoulli's principle, in front of the airfoil, we should have a stagnation point and low flow, essentially all around where that high pressure is. So we got a stagnation point here. All right, and then as you get up towards the top and bottom of this airfoil, we end up getting lower pressure. Okay. And then we should have faster flow going over the top. So if I were to extend these pressure contours here, we should have something that looks like this. Low pressure, and then on the front end here, we end up having almost a circular pattern here for the pressure contours. Okay. Now, in terms of what the flow is going to end up doing here, and what we're going to do in Paraview is we're going to set up some seed points to trace out a few streamlines, and then we'll color code those streamlines according to the magnitude of the velocity. So you'll be able to see the low flow, and then of course we'll have the pressure visualized on top of that airfoil here, so you'll see the corresponding low flow, high pressure, so you'll be able to demonstrate Bernoulli's principle for irrotational flow. And what we should see is, because the flow gets faster, we should see a bunching up of these streamlines over top of that low pressure region above the airfoil. All right, so I'll just walk you through quickly after we get that connection done, which it looks like we are connected now. Yeah, we absolutely are. You can see now in the memory inspector, we got our server set up and it's running on PV node 0. So let's go ahead and pull in the OpenFOAM data. So if you click on open now, the nice thing is you now have two windows in which you can navigate for bringing in data you want to visualize. So you have up on the top here is on your local client, and then the bottom window here is for the server. So here we've got our airfoil NACA0012 demonstration that's up on the server. Let's click on that NACA0012.foam file. Let's get that in, and let's first just start by looking at the airfoil mesh. And we're only going to want to look at the pressure. Okay, so go ahead and hit apply, and we'll clear those messages. So let's take a look in the positive Y direction, and I'll kind of rotate this a little bit so it's a little bit easier to see. So up on the front again, we still have that high pressure region. Flow is going from left to right over here. Now what we want to do is bring in those velocity points. So we'll have to open up that same .foam file one more time. And get another view in our window here. So let's use the internal mesh, and this time we only want to bring in U, which is a vector field. Let's go ahead and apply. And at first it's going to show the whole mesh in here, so bear with me one moment here. Let's click on that streamlines viewer, and then you can hide that internal mesh. So on the streamlines, what we want to do is basically have some seed points set up and integrate only in the direction of the flow. So you'll set that to forward. And the streamline length, so this airfoil really is only 1 meter long, but the domain size is about 150 meters. We don't need streamlines to go that far. So let's just set this back to like 3. That should be fine. And then in terms of the point, the front of the airfoil is basically at x equals 0. So let's stick the seed points somewhere just out in front. Let's say minus 0.1. And for the Y point, we need to set that to minus 0.5 and minus 0.5, and then we'll just vary the z component for the start and end here. So we get, let's say minus 0.5 up to 0.5. Let's see what that does for us. So if I were to kind of look at this head on here in the positive x direction, right, we've got a line that's basically cut halfway through that airfoil, top to bottom, and along this line we'll be setting up seed points for visualizing or for tracing out those streamlines. So that should be good. Maybe I'll make it a little bit shorter. Let's go 2.5. Yeah, that'll be a little bit nicer. And then in terms of the number of points, we certainly don't need 1,000. Let's put this maybe 30. And the other thing we want to do is, let's see here. Let's go ahead and trace this out and see what we get to start. And then what we're going to do next is just set up the coloring on those streamlines. So yeah, like you can see already is where the high pressure is. In front of that nose there, we've got a stagnation point. We've got a bunching up of the streamlines up above. Let's change the coloring to the velocity magnitude, and let's edit that color map just so we get something a little bit nicer, nicer to work with here. So let's change the color scale, bump that up to like 150 and down to about 300. So we'll rescale, and then let's change out the color map, and let's pick something that's a little bit more vibrant so we can make out what's going on here. So you can see in this blue region here, we've got low flow corresponding to that blue value here on that color map. And then as you get up over top of that airfoil, we're turning into this yellow color, so we're speeding up. So, I mean, essentially at this point, we've got some demonstration of Bernoulli's principle, but of course, you've also just seen how to connect Paraview server on the cloud to a Paraview client locally and do some rendering. Of course, there's a lot more stuff you'd want to do for scientific validation here, but this should get you started in that direction. Well, I hope you guys found this useful, and I would encourage you to subscribe to what we have going on YouTube. We have tons of tutorials planned for you guys, not just around CFD, but around a lot of other things concerning cloud and HPC. Thanks again for joining, and I hope to see you guys next time.